So thanks for coming. Initially, I'm going to talk about some work that we did recently in Lasky structure, but maybe we thought that it would be to the physics group, since it is about constraints of simple field inflation from the post-galaxy survey. So we split the talk into halves. I will introduce the inflation part, and then Misha will talk about the Lasky structure part. So let me start. So for current data that we have so far, we have an idea that the primordial universe is very close to being a Gaussian universe. So in the case that if we focus on the single field inflationary models, the Lagrangian for a Gaussian universe, which is only quadratic action, then sorry, the action for Gaussian universe is only the quadratic action. It takes this form. We have the action for the graviton, and then we have the degree of freedom that we call the moving curvature perturbation zeta, that the scalar degree of freedom and is the source for the density fluctuation in the late universe that Misha will talk about. So the parameters that we have in this quadratic action are the following. So we have epsilon that I define as minus h dot over k squared. It tells how much during inflation we are deviating from the zeta expansion. Then we have, of course, upward that enters in the scale factor, double rate. And then we have also the speed of sound of this scalar fluctuation. So one could ask, the question we can ask try to measure this number, then epsilon, upward, and speed of sound. Now, what are the observables that we can use to actually measure these numbers? So in cosmology,
I thought that the speed of sound comes in the kinetic term versus the...
Oh, I didn't put it. Oh, sorry. This is embarrassing. I forgot. It must come there.
We're all term in the Lagrangian.
So yes. So the observables we can use to try to extract information on these numbers are correlation functions of this zeta and gamma and the graviton field at the late times. So as the modes leave the horizon. So as maybe people in the audience already know, for example, if we were to measure, hopefully one day we will measure the two-point function of gamma, this will give us a handle over the energy scale of inflation, so on upward. But then what about the speed of sound and epsilon? So since we only measure correlation functions of zeta late times, we cannot disentangle between the overall amplitude of the fluctuations, if you want, and how fast they propagate. Indeed, if we were to measure the two-point function of zeta, this goes h squared over m squared epsilon cs. So we cannot disentangle between the two. And the way actually in which we are able to disentangle is actually that we need in this case to look at the corrections to this action. So look at the small non-Gaussianity that are on top of this leading pitch that we have over our universe. So let me discuss how we can describe interactions single field inflation. So single field inflation is characterized by having some scalar quantity that has some vector expectation value that depends on time and tracks the evolution, the history of our universe. It has the evolution of the energy density. It tells us when inflation ends. This scalar quantity will have some fluctuations on top of it. So what can we do? We can use now a trick to write down an expression for the Lagrangian inflation in a very model independent way. Is you can use the coordinate invariance general relativity to take the scalar quantity as a clock. So you put the scalar quantity to be the time coordinate. So we break explicitly the time difference with this invariance of general relativity, and we put the scalar degree of freedom inside the metric. So in this unitary gauge, then our action for single field inflation can be written by collecting all the possible terms that are invariant under all different fields, like for example, of course, the Einstein-Hilbert piece, and also terms that are invariant only under spatial different. And I've written here some. And for example, here I have the second line, there are some dots. There are many other terms that we can add that are higher order, for example, in perturbations around an FRW background. For example, you can see here that this term starts a quadratic order around an FRW background. This starts a cubic order. These can be terms that we can add that start higher order in perturbations. The only terms that could start a linear order are the first line, but the coefficients have been chosen in such a way that the tag was cancelled. This literally is an action for the fluctuations in a single field inflationary model. Very agnostic, model independent. Now, in principle, the action for this is actually very complicated. One can expand in perturbations, and the complications rise fast. But there is some trick that one can do. One can, now, as I said, the scalar degree of freedom is being eaten by the metric now is the zeta variable. What one can do is reintroduce it explicitly by doing like a Stuckelberg trick, doing a broken time diffeomorphism, and introduce the degree of freedom, scalar degree of freedom explicitly. Now the scalar degree of freedom will be pi. Call it pi. The advantage of this is not apparent, but if we recall immediately, essentially the Boston-Boson equivalence theorem, we know there will be some range of energy scales for which we can go in the so-called decoupling. We are in the decoupling limit where this pi degree of freedom is decoupled from the matrix. We can read it or with it separately. And given the constraint that we have on single field inflation and up on the data, this limit is actually very good, so we can take it. And in this limit, the action for the scalar degree of freedom in single field inflation simplifies dramatically. It is very simple because of this form. Well, actually, I have to read it. I don't remember by heart. It was right. This is the quadratic part, and then there are the interactions. There are two kinds of interactions. One is one-time derivative and two spatial derivatives. And then there is one that has three-time derivatives. And the coefficient CS, that is the speed of sound for pi, the coefficient CT in the tail, can be written in terms of the coefficients M4 and 2 and M3 there, and the expression is here is not very illuminating, but it would be just for completeness. So now there is a final ingredient that we need. We have the simple action now for pi. What we observe is, as I said, zeta, the correlation function of zeta, and we can use the fact that there is a very simple relation actually between pi and zeta at late times. So as the conformal time becomes smaller and smaller, mostly the horizon, we have that zeta is proportional to pi plus some other epsilon and other slow terms. These are slow suppressed terms we neglect in our leading approximation. So the relation between eta and zeta and pi is very simple. So if we compute the correlation functions of pi, we get for free the ones from zeta, the ones for zeta, and we can see that indeed it is true that by looking at, for example, if we constrain the tripping function or the non-Gaussianity coming from this operator, we have an end along the speed of sound. We vary the degeneracy that exists at the power spectrum level. This is then why I think it is interesting to look at this from the non-Gaussianity, even the single field inflation case. So, okay. Well, we parameterize the non-Gaussianity. So what we look at is the simple probe of the simplest probe of the non-Gaussianity of zeta is the tripping function, as we were mentioning, which we can rewrite in terms of the base spectrum in the following way. So it is a polar base spectrum in the following way. So we use the fact that in the tripping function, which is rotational invariance, the free momentum form a closed triangle. There is a clear delta function here. And then we have the base spectrum, which is a function only on the amplitude, the moduli or the momenta due to rotational invariance. And then we, for our analysis, we used an expression for the base spectrum, which is by now default, if you want, in the literature, which is the following. You write because it allows me to use a parameter, which is a parameter on which we put the constraint. So it is FNL, some shape function where this number here is the amplitude of the power spectrum of zeta. So this is what we measure very well from, for example, the Planck satellite. So delta square zeta is k cubed power spectrum. So then at a fixed delta square, the amplitude of the base spectrum is from this FNL, controlled by this FNL parameter. And there will be now two FNLs, one for this operator and one for the other operator. So we have FNL and FNL by dot cube, and they will have the corresponding shapes. Now, these shapes can be computed, for example, level calculation from this action. They have some properties, but one would use those shapes to do the analysis, but we don't actually do this. What we do is something different. We introduce two templates that are constructed in such a way that one can reproduce these two shapes, but in a simplified way, in a way that is simpler for us for the analysis purposes. So we in principle have these two FNLs and these two shapes, but we define other two FNLs in two templates, which are equilateral and orthogonal FNLs with corresponding shapes. When do we do this? And the reason is mostly a practical one. Let me define first what are the properties of these templates, and then I will explain in more detail why we choose to do the analysis in this way. So first, these templates have a property that I will not write them down in the specific form because it's not very long and it is not very important to write them down, but the properties are the following. So first, they are property A, they are separable in K1, K2, K3. This doesn't happen in general for the bispectra for the shades that come from a computation of these two of these operators in the non-Gaussianity coming from these two operators. The bispectrum coming from those will not be separable. This for us, it's actually helpful to have them to be separable. It speeds up some of the parts of the analysis. And this template is also another property, which are the correct behavior in the so-called squeeze limit. When I have one of the three modes in the bispectrum that becomes much smaller than the other two. So in this limit, there is a property of there is a constraint one must satisfy. The bispectrum of zeta must go as k3 over k1 squared times the 2 power spectra for the long and the short modes. This is a generic feature of single field inflation in the scale invariant drop is low suppressed term case that we're considering. We cannot have a squeeze limit where there is a power here less than 2. The motivation here for this is something generic happening single field inflation. The motivation you can see it maybe already from this Lagrangian. Like you can see these interactions, and let's consider now that we have we take two of these pi's to be short wavelength and one to be long. So we modulate by a long wavelength pi the action of the short modes. You see that we take a long wavelength pi which is homogeneous and time independent. There is no modulation because pi always comes with derivatives. Essentially, this tells me that any effect must come with this power 2. If there was an effect, if essentially pi would appear without derivatives there, I would have a squeeze limit where k3 over k1 to the 0 would have appeared. So this doesn't happen. Single field inflation is very more important, more general reason for why this is the case, but for now this is enough. And this template that we have satisfies this property as well. So now the interesting point is that one can actually show, and I find this template, but actually one can show that they are linearly related to the FNLs from these two operators. So precisely, one can find that, well, now the numbers I have to check because I don't remember, there is a linear relation. This is not an exact relation, but for our purposes, given our the current errors that we have from Nonzero and also from the CMB, this is more than enough. We can relate the FNLs of the templates to the ones from the operators via a linear transformation. So if we put constraints on these simplified templates, so separable, via this simple relation, we can use constraints on the amplitudes of the non-Gaussianities from the effective theory, well, the single field inflationary reaction, and then constraints, for example, this parameter C tilde 3, and more importantly, maybe the speed of sound.
But can you say again what separable means?
Right, yeah. Let me make. It means, for example, if I look not at the template, but at actually the non-Gaussianity is coming from the calculation from these operators. For example, they have a contribution. Well, they are this form of some p, and then there are some polynomials of k1, k2, k3, which is symmetric. Of course, since I'm looking at three function of the same field. So this polynomial is fine. I can, well, it is a polynomial. So when this one I cannot write as it is not a polynomial. So this does answer the question? Or?
Separable is a mathematical property of the function.
Yes, I just meant that they cannot write it as a product of functions of K1, K2, and K3 separate.
Oh, I see.
Sorry, maybe this. For example, let me just say, suppose that
Yeah, I understand. So, for
Okay.
example, the product of spectrum is not that kind, like
Yeah.
what you have over there.
yes. For example, there are some tricks to make this like separable. For example, if I write this as an integral in some dt of e to the minus, now I'm screwing up the range of integration, but okay. K1 plus K2 plus K3, I can then write it as a product of three functions of separate K1, K2, K3 up to an integral. This is just it is a bit of a complication when you actually want to compute some of the terms that Misha will talk about. Maybe he will not really deal on this, but having a separable way that a form that is directly factorizable in that way is easier for us. And also there is.
So let me understand. So your equial and orthogonal are separable functions.
Yes. Yes.
And what does the last equation mean? This equation with the matrix. I mean, it's not that the shapes are not related by a simple matrix.
No, this is this is a bit. Let me. How can I explain? They are not related by a simple matrix. One can define. The best way to see, well, the best way to say it maybe is that one can define a scalar product between shapes. And precisely, well, I want you to use the plot later, but essentially, let me just say, shape without also generality, one can plot shapes on this plane of ratio K1 of K3, K2 to K3, and in this triangular region. So let's call this region V. So one can define a scalar product between two shapes by, for example, x1 and x2 are the ratio of the momenta.
It's an infinite dimensional space.
Yeah, exactly. So yes. So in principle, this is an infinite. So in principle, this is not. There will be an infinite. If I can, I don't even actually know how you find the basis of this space. But suppose that you find, I think there will be an infinite, of course, matrix. But for us, we find that even this simplified relation, so only with truncating this infinite dimensional matrix to a 2 by 2, it works very well to reproduce the behavior of the shapes. Well, the behavior of the pi dot and pi square and pi cube shapes via this equilateral and orthogonal over a vast range of this region here. Actually, the pi dot and pi square is reproduced to, I wrote it.
Right, so the claim is that if you consider the shapes, the correct shapes, so then you can express them as these shapes plus something else. The something else is small.
Yes.
Okay.
Yes. And I want to say that this is especially true for this one. This is like a relative difference of 0.004, which is actually quite amazing. Maybe there is some deeper reason, but okay. So I wanted to actually wrap up to leave to Misha. So now we put constraints in this, putting constraints on this equilateral orthogonal, we can translate them to this. And I wanted just to conclude by showing a bit that I will just show these two plots. These are the two artist rendition of the shape. This is the equilateral one. It takes the name because it fits in the equilateral configuration, which is in this angle here. And one can show that in that way. Maybe you won't see it from here, but it vanishes in the squeeze limit. And that one is the orthogonal. And now actually, since I introduced the scalar product, I can say why it is orthogonal, because it is defined to have a zero scalar product in the equilateral one. And if you see that it again is normalized to 1 in the equilateral configuration, but it fits actually in the folded limit, which is that one. So that was my introduction. I then leave to Misha. Let me move up the.
Pull up to answer the question why these two shapes they seem to capture this behavior. I think that in the end, what matters for this color product and also for that analysis is that only you capture well the triangles at which the shape is picked, and that's why like these two shapes they have the same property. Like one of them peaks at the collateral configuration, the other one is peaked at the folded configurations. And if you like approximately just mimic this behavior with these approximate shapes, then this will be fine. So works very, very well. All right. So yes, Giovanni explained this story how the seeds for structure formation are generated during inflation. And then, of course, if we want to probe, then if we want to test primordial non-Gaussianity, we need to look for it in the data. And well, looking at the data is complicated because of many reasons. The best constraints so far they have been obtained from the Planck CMB data, but Planck is well, the CMB data in general has several limitations because well, essentially you don't have access to that many modes. You're limited by having only modes on a sky in a sort of projected state. And much better constraints you can get by observing galaxies and trying to see non-Gaussianity to the level of galaxies. But for that, you need to model very well their clustering. And this is also done by applying effective field theory ideas and essentially by using the effective field theory of Plaschke structure. So let me, I'm going to briefly overview the EFT of LSS and first of all show how we can use it to describe the nonlinear clustering of dark matter. Then I will move on to galaxies, which are the actual observables. And then finally, I'll combine these things together and also the primordial non-Gaussianity and show how we can use the galaxy surveys to obtain constraints on inflation on this non-Gaussianity. Right, so the cartoon picture of what is happening will look like this. We start with some patch of our universe that has this primordial curvature fluctuations at zeta. And then our universe expands, and these fluctuations, they will essentially undergo some cosmological evolution. At some point, they seed the dark matter fluctuations, and dark matter collapses and forms structures like galaxies. So together, this all leads to galaxies. These galaxies we characterize by the overdensity field, delta galaxies, so its density, what we better say, the number density of galaxies, right over the number density. And this is a function, the observed distribution of galaxies is a function of these initial conditions. And we have to understand how these two distributions are related. And of course, at face value, this seems to be a very complicated problem because if we look, let's say, at dark matter halo, so typically the situation that we observe in galaxy surveys is the following: we see a galaxy, and this galaxy is sitting in a dark matter halo whose typical size is of order, let's say, 10 megaparsecs, so R halo. And of course, this galaxy formation is a very complicated nonlinear process that we cannot model from first principles. But however, if we zoom out and look at longer scales, at bigger scales, we'll just see that the distribution, like every single halo looks like a molecular in our universe. So our universe looks like a field, like a space field with a gas of galaxies. And in this situation, in fact, for distances which are longer, bigger than the size of the halo. So here we're talking about distances of order 100 megaparsecs. We can actually describe the distribution of galaxies as a perfect fluid. And well, it's an effective fluid, which is what turns out to be imperfect, in fact. But it's important that this fluid is non-relativistic, because the relativistic effects, they become important only on even larger scales when we reach the size of the our universe. So roughly on the scale of the inverse Hubble parameter, which is a few gigaparsecs. So together we have this nice scale separation. We have this air halo, H to the -1. And our galaxies, well, the galaxy surveys, they mostly map our universe on the scales of order 100 megaparsecs. So we live here in this regime, where we can build the effective fluid description. And the small parameter in this expansion will be, well, essentially this air halo over lambda, or sometimes this air halo is also called the nonlinear scale, R nonlinear over R. So we're just doing the distance expansion. And since I mentioned fluid, okay, fluids are characterized by the mean-free path. And here this size of the halo is planar row of the mean-free path. So let me now write down the equations of motion. So for fluid, we know very well how to write this equation of motions. Our long value degrees of freedom are the overdensity field, delta rho over rho, and the velocity. So I discussed this picture, with galaxies and dark matter, but let me first focus on the case of dark matter. So I will discuss galaxies later on. Let me just consider this clustering of pure dark matter to begin with. Then this dark matter is described by the usual continuity in earlier equations. So dI here is the peculiar velocity. So this is the velocity fluctuation. Then I have the earlier equation, which contains nonlinear terms due to the convective derivatives. And then, as I mentioned, it's important that this earlier equation also has some effective strength tensor that depends on long wavelength degrees of freedom, and also gradients of our fields, and so on and so forth. Then we need to write down the Poisson equation, describes gravity. So this is our system that describes the clustering of dark matter in the, in the regime where the nonlinear nonlinearities are small. So on this scales larger than the size of the typical halo. And those are the equations of motion, and also we have to specify initial conditions. And so we need to provide the values of our fields at initial times, and these values are given. So delta t equals 0 is going to be given by this zeta times what is called the transfer function that captures the evolution before, from inflation to the moment after a combination, where the initial conditions for structure formation are seeded, because we do have some evolution in between. For instance, you know that dark matter undergoes the logarithmic growth on the radiation dominated era, and this is why we managed to form structures by now. And all these effects are precisely captured in this M function. Well, typically we do it in Fourier space. Right, and this field, so naturally it has the Gaussian distribution, and also if we have non-Gaussianity, it might also have some non-zero bispectrum. So altogether, the initial conditions for the system in terms of statistics, they are given by a two-point function of this delta zero prime. Strip of the delta function, and also I can have the initial three-point function. And this bispectrum is precisely, well, it is related through this transfer function. It is related to the bispectrum of zeta that we want to probe. Yes, that's great. That's a great point. So indeed, in principle, we have a second field, but in cosmology, at late times, we have only one degree of freedom, which is a growing mode. So the velocity will be fixed by the same initial conditions. In other words, for adiabatic initial conditions, you only need to specify one field that sources everything. So in other words, so for velocity, yeah, you can first of all get convinced that only the scalar part of the velocity matters, so only the longitudinal. And in other words, and then we only care about the velocity derivative. And in the growing mode, the velocity derivative at early times is equal to the density. All right. So now, yes, let me say a few words about linear theory. So if we take a look at these equations. If we neglect the viscosity, and also if we neglect these convective nonlinear terms, then the system has a solution in the form of growing mode, I just mentioned. So this system at linear order, linear theory, has the solution given by delta linear is equal to delta zero times the growth factor on T. So this growth factor is something, if our universe was matter dominated, then this would be just a scale factor. And this precisely just reflects the fact that matter dominated area, on matter dominated era, the perturbations, they grow in a scale independent fashion and proportional to the redshift. And the same is true for the velocity divergence field. And the curl, so gravity doesn't source the curl field, right? Because you have only the gradient here. And because of this, the curl decays during the cosmological evolution, in the end, it doesn't matter. So yeah, we only need to worry about the longitudinal part of the velocity field. And these fields, they have essentially they have the same distribution as the initial fields because they're only different by multiplication by the growth factor. So in other words, this delta 1 prime will be given by the linear matter power spectrum, which is also denoted as P11. And then the bispectrum due to primordial non-Gaussianity, it will be given by P111. Here, I plot how this power spectrum looks like as a function of wave number. So it has this, so P11, this linear power spectrum, it has this kind of characteristic shape of the turnover, and the turnover marks the period of the matter radiation equality. Just because the evolution of perturbations is different during the radiation stage and matter stage, and these perturbations, they enter the horizon during the radiation stage. And well, because of this difference, we have this peak. But essentially, in galaxy surveys, we always see only this part of the spectrum, and this part can be well approximated as just some power law as k to the -2. And in other words, this
the scale invariant spectrum, what will it be in this?
the scale invariant spectrum would be k to the -3. And you have this k to the -2 precisely because of this logarithmic growth during the radiation diminishment. So actually, this part is k to the -3 times log k. But for a limited range of scales, this log k looks like k. So together, this power spectrum behaves like k to the -2, approximately. Well, this just to give you some idea how it scales with momentum. So together, this P11 approximately goes like k over k nonlinear. In this simple power law case, we have only one scale that controls the power spectrum. And it's the same scale as the scale of nonlinearities, because you can see that when k becomes equal to k nonlinear, the power spectrum becomes order 1.
Could you explain again why there is a maximum? So what happens at low?
Oh, yes, very good. So very roughly, so if we neglect this logarithmic growth, then this part will be just given by k to -2. This is the scale invariant spectrum. Those are the modes that enter the horizon during the radiation domination. And this part are the modes that enter the horizon during matter domination. And for these modes, we have so in this part of the spectrum, the gravitational potential is constant. And which means that the delta, the density field, will be k squared times constant. This is just due to the Poisson equation. Which means that the power spectrum, P11, will go like, so it's delta squared, it will have k to the 4 times the power spectrum of delta. Sorry, the power spectrum of phi, the power spectrum of initial fluctuations. But this one is scale invariant for good precision. So altogether, it will go like k. So this asymptotic is k.
Is this basically saying that the modes enter and they start growing? So something that enter.
Yes, yes, all these modes, yeah, they just, when they enter the horizon, they just start growing like constantly. But really, it's due to the fact that, well, yeah, on large scales, the gravitational potential is conserved. And here already the nonlinear evolution, well, sorry, the evolution of modes during the radiation domination changes the behavior on very short scales, and that's why you have this k to -3. All right. So yes, so the amplitude of density fluctuations is, let's say, the variance of density fluctuations is the integral over the power spectrum, and you can see that in the scaling universe it will scale like k over k nonlinear. So just multiply this by k cubed. So altogether, in other words, so I introduced this long distance degrees of freedom, and I said that the small parameter is k over k nonlinear, and in fact, all this, density and velocity also secretly, because of this relationship, they scale like k over k nonlinear. The density field scales like k over k nonlinear to the 1/2. All right. So this was linear theory, but now let me take into account these nonlinear effects, nonlinear terms, including nonlinear theory. So we compute the nonlinear corrections perturbatively by essentially Taylor expanding over over this delta 1. So we'll write down delta nonlinear is given by delta linear plus something that this is called the nonlinear kernel, is determined by the equation of motion. But at this point, let me just assume that we write the following ansatz. So delta nonlinear is delta linear squared, plus delta linear cubed, plus and so on. And the same for the velocity. Delta 1 plus delta 1 squared, plus and so on. And when we plug this ansatz into the equation of motion, essentially the equations of motion, they will fix these kernels that appear here. So these kernels in Fourier space, they would look like this, something like constant plus, so it's a Fourier convolution in the end, plus something like K1, K2, K1 squared, plus and so on. So it's an order 1 in terms of momentum. But in principle, you can just plug this into the equation of motion and obtain this. See that at every order in delta, this expression solves the full nonlinear equation. And now, so now we know the distribution of delta 1s of our linear field, and we can compute the correlation functions. And quite naturally, this expansion can be reproduced, that can be interpreted as Feynman diagrams. So in other words, when I now square this delta nonlinear field and compute the expectation value using the statistics of delta 1, I will get the following. So I will get, so this is the usual linear theory expression. And in terms of Feynman diagrams, typically we denote with some kind of box. So this is linear propagator, plus I will have the term that schematically comes from two contractions of this contribution, and then it will produce a loop integral that looks like this. And then there will be a term of this structure. And finally, because I have a non-zero 3-point function, I will generate a term from the contraction of this linear density and quadratic density. And so this term will contain the pi spectrum. And all these terms, they have names, they have price. So this is P11, this is P22, because you have twice this second order field. So P13 and this one P12. And this is the one which contains FNL. And here, schematically, I show how these corrections look like. So this P12 and P13 altogether, they go like this. So at some point, you see that these loop corrections, they become bigger than linear power spectrum, and perturbation theory breaks down. But on larger scales, they're still smaller than the linear theory, and perturbation theory is well defined. And this non-Gaussian loop correction that is generated by FNL, it has a different scale dependence as the usual matter nonlinearities. And this is something that helps us separate these two effects at the nonlinear level. Right. Also, so here I computed the 2-point function, but also the nonlinear evolution generates a non-zero 3-point function. I will get the bispectrum, which is first produced by the. So even if I have the purely Gauss initial conditions, this coupling will generate a non-trivial bispectrum from this, essentially stemming from this term. P112. It's also called, with some abuse of notation language, is called the Gaussian bispectrum. because it just comes from the Gaussian initial conditions. But also I will have the standard. Well, I will also have the term that is produced by FNLs. 111. And in the galaxy survey, what I see is typically sum of these two corrections, and also I can have some nonlinear loop diagrams, something like this. So these ones I can also compute. So for them, I will have to go to higher orders in these expansions. But in principle, now we know how to iterate and go to higher orders in this EFT for dark matter. So what happens now with galaxies? Galaxies trace dark matter, but the exact relationship between them is, well, it's not clear. The two must be correlated, but the way how they are correlated is also intrinsically nonlinear. And I guess maybe to give you some idea how this happens, we can consider a toy model of galaxy formation, which goes like this. So imagine that we have some position here, position coordinate, and we have some dark matter density fluctuation. So we have some long mode, and we have some short scale fluctuations. So whenever even in the purely Gaussian theory, you can have some large fluctuations. And whenever the fluctuations at some scale become order 1, so this is density, and let's say there is a critical value, which is order 1. So whenever the fluctuations, some distance, some patch of the universe become order 1, my dark matter collapses, undergoes nonlinear collapse, and forms a galaxy. And in this simple model, you can see that the probability of forming a galaxy depends on the short scale power in this small patches of the universe, and it will be enhanced if the short scale power is modulated by a long wavelength, so delta long, by a long wavelength density fluctuation. So in other words, then the observed density of galaxies from this simple picture, you can expect that on large scales, it should be linearly related to the density of dark matter, to this density field that we're computing using the fluid equations. And of course, since everything is fully nonlinear, you can imagine corrections to this result. So you will have something like quadratic contribution, and also this probability to form a galaxy would depend on the local tidal field. So you can have something like pi Newtonian squared, and so on. So how does non-Gaussianity enter this relationship? So from this picture, you can see that if you have some extra correlation between long and short modes, that is typically something that what non-Gaussianity does, then it would enhance this correlation, would modulate the short scale power spectrum and also increase the probability of galaxy formation. And to see how this happens, maybe the simplest calculation you can have is the following one. We need to write down the partition function for galaxies. We have the integral over the path integral over all initial configurations. So I denoted them delta 0. And then we have the exponent of the Gaussian part plus if we have some primordial non-Gaussianity, we would have the following contributions. So integral to 1 Integral, so Q1, Q2, Q3, then has the bispectrum, the initial bispectrum, B111. Q1, so now if I use the method of regions, and if I split my density field into long and short domains, okay, for the Gaussian part, I will just have, the long part, the short part.
Would you say what this quantity is? What is the left-hand side?
Say it again?
What is the left-hand side of this equation?
Well, this is good. Yeah, this is the partition. In principle, everything what I was computing, you can extract from this partition function. And then this delta will be functional. This delta is 0.
Functional delta.
Yes, it's a functional, right? It's a functional of delta. So you can, using this functional, you can fully reproduce this calculation. Yeah, I'm just showing it to, I'm writing this to show you that at least in order, the way how the bispectrum affects the, distribution of matter will be through a squeeze limit. And to see this, so I have this initial distribution, and then I can split this integral. So it's integral over Q1, Q2, and Q3. I can split now this integral into the long and short domains. And then, here I also have the delta function. It ensures momentum conservation. And because of this one, once I have one mode, so one of the modes, let's say Q1 is going to be K short, Q2 is going to be K long, which is much smaller than K short. And then the third mode, because of this delta function, will be proportional to K short, minus K long, order K short. So in other words, when I split this integration and use the momentum conservation, I will see that essentially this part in my statistical weight so it will produce the correction that goes like this. I will have K short, delta of K short squared, delta of K long, K long, K short, K long, K short, K long. So this part looks exactly like the Gaussian weight. So now I can rewrite this as an effective Gaussian weight where the power spectrum is modulated by the squeeze limit bispectrum. K long, K short, K long. So this calculation just shows you that the relevant quantity here is the squeeze limit of the bispectrum that Giovanni introduced. And in particular, so if I do B555, or sorry, it was zeta, or now zeta. K long, K short, or P, so zeta, K long, short. The single field models that Giovanni discussed, numerically, they have the scaling like k long over k short square times FNL. So the squeeze limit is suppressed by k squared. Whereas for the in the case of local non-Gaussianity, order 1, a number times FNL. Right, and this calculation just shows you a simple physical picture. If you have primordial non-Gaussianity, it will modulate the short scale power and also affect the galaxy formation. And in order to reproduce this result at the level of the initial conditions, we need to add the following terms in our galaxy bias relation. So for the local non-Gaussianity, in order to reproduce the squeeze limit of the bispectrum, we need to add, well, actually, we need to add the Baryon potential, let's say zeta. For the single field terms, we need to add zeta local, zeta single field. We need to add this Laplacian of zeta to reproduce this suppression in the squeeze limit. So altogether we have, but this is just a trick, right? Because of the increase principle, your local observable cannot depend on the gravitational potential. It's just a trick to reproduce this story with the initial conditions. Right. So altogether we have this. So primordial non-Gaussianity affects the structure formation 3 ways. It generates these loop corrections to the power spectrum. It produces the contribution to the bias spectrum, and also it generates this extra bias in the structure formation. And altogether, now we know how to compute all these effects, and we put them together and finish now them together. And essentially we use the galaxy power spectrum data from the Baryon Oscillation Survey and feed this data with all this, power spectrum and bispectrum with all the nonlinear corrections that come from these pictures, and we obtain the following results. Here I summarize some of the properties of the survey that has 2 million galaxies, stretch over 10 square degrees, covers some area Z. So we compute the bispectrum, power spectrum, fit with everything, and we obtain the following constraints.
This data is just the position of all these galaxies.
Yes, exactly. So we observe on the sky, right, 2 angles and redshift.
And the mass of the galaxy, we care about that?
Well, we don't really care about that, but these are typically, the halos, we know roughly that is 10 to the 14 solar masses. But in principle, as long as the galaxy sample is uniform, we don't have to worry about the exact position of galaxies. For us, it's just like a particular fluid. So these are so-called red luminous galaxies. They have similar properties, massive galaxies. Right.
So you're plotting a particular kind of galaxy?
Yes. In this analysis, we use one particular kind of galaxies. Because if we have 2 kinds of galaxies, it means that we need to do delta galaxy 1 and delta galaxy 2 for each of them.
Okay, good.
We have to introduce all these coefficients. So we keep these coefficients, we marginalize over them. So in the end, we obtain the result of FNL lateral is equal to 60 plus minus 300. So we did not detect FNL collateral, and also we did not detect FNL orthogonal. But we put limits, which right now are something like factor of 5 worse than Planck. But Planck is, Planck will not improve much in the coming years, but with large-scale structure, we'll improve these limits by a factor of, let's say, from 5, at least 5, from 5 to 10 in the course of 5 years. So we'll be better than Planck. Just doing the same kind of analysis on the data that will come soon from galaxy surveys will improve these limits by factor of 10 essentially, and that's why we're excited about this result. And very soon we'll be able to, answer some order one questions about inflation that Giovanni mentioned. So I think that I presented this interesting interplay with the different EFTs that we use to constrain non-Gaussianity, and hope that you like the things we're doing. So thank you.
Let me see if I understand. So here you had these two possible behaviors, right?
Here, right?
Does one of them correspond to one of the two FNLs?
Yes, exactly. So in the case of local non-Gaussianity, if I want to reproduce, so the squeeze limit doesn't have any suppression. It's just essentially.
So it's basically bound on this order for one.
Right. And having some model, something similar like this, we can actually even compute this like order one number. So we can compute this so-called non-Gaussian bias. But principally, to reproduce this picture, in the case of local non-Gaussianity, in our bias expansion, we need to add this contribution. So that is only proportional to the curvature factor.
This is something we don't expect in the single field model.
We don't expect.
Yes. So we have this K square. So essentially, this suppression K long or K short that comes from this kind of derivative interaction that's dictated by the spontaneous symmetry breaking, similar to like fines. Right. But in multi-field inflations, which are typically predict the FNL local, so there we don't have this constraint, and that's why we are allowed to have this like non-soft behavior.
So of the two bounds that you had, which is that the 100?
Well, this 100 were This 100 were bounds for on this FNL collateral orthogonal and for the local. So FNL local. We're currently doing this analysis, but the preliminary results is that something plus minus 20. Roughly.
And the something is of order 20.
Yeah, something is of order 20. So, right. So local is more complicated than these things, just because we have more nonlinear terms. So you have this term, and also you need to add, for instance, term that in the galaxy expansion, you need to add term that has NLPC term that looks like this, for instance.
Yeah.
And many more. So because of this, so zeta is scale invariant, so it doesn't have any scaling K or K nonlinear. And therefore, we're allowed to add many terms, of this kind, and they will be important at, let's say, one order in terms of K or K nonlinear. And that's why we have to keep track of many of them for the analysis of the local non-Gaussianity. And for the single field non-Gaussianity, we have this additional K square suppression. And that's why this term is already one loop. So there's only a finite number of terms that we have to worry about. And that's why this analysis just explains why we have these results right now. And this is still in progress just because we have more nonlinear corrections that we have to compute.
And suppose in the far future, you look at the whole sky and everything, let's say you have an infinite, you observe everything. How much are you supposed to go in this analysis?
Good. So
not the next 5 years, whatever the observations are going to be, but let's say the maximum you could possibly measure observing, limited only by the fact that the universe is finite.
Right. Cosmic variance limited. So we'll be able to get FNL local better than 1.
Yes.
And at this point, we'll be able to say, so now we have 20, and we need to, let's say, if we have it 0.1, then we'll be able to, let's say, rule out the simplest multi-field models, things like Urvaton, for instance. And well, the other way around, if we detect one of them, then it will be, let's say, strong evidence for single field inflation.
Well, you could have also these other ones without the single field.
Yes. So
the two that you listed.
the two one, right? Yeah. Good. Yeah, there are models of inflation, for instance, multi-field, but predicts FNL collateral. But for this, we need to measure the whole shape now. So this whole function of Giovanni S, K1, K2, K3, because then this will be different. I mean, typical model that does this, let's say, called trapped inflation. But its shape is true that it's also picked at the equilateral configurations, but its full shape dependence is different from the one produced by this term. So this one is produced by this pi dot and grad pi squared. It will be different, so we'll be able to tell them apart in principle.
And if the speed of sound is very close to 1, let's say the standard inflation, so one of them is not supposed to be there.
I think in that case,
actually, yeah,
both of them are very suppressed.
But both of them are not there.
Yes, so in that case, slow
Oh, right,
roll, if you are in slow roll inflation, these non-Gaussianities are all
Order 1, right? Are they numbers of order 1 for these two, or even smaller?
no, they are smaller. The non-Gaussianities in slow roll inflation are as they are slow roll suppressed.
Okay, yeah, fine. Okay, yeah, they're all order.
Right.
So that's the worst case scenario. If that's or depending on the point of view, it will be very difficult to measure those non-Gaussianities if they are slow roll suppressed.
Right. So I think that here we keep in mind mostly non-minimum models like the DPI inflation or something like this that has like naturally produced some derivative interactions.
Yes.
Okay. So now people say the speed of sound is let's say bigger than 1/12 or something like this.
Mm-hmm. Yeah.
So what do we find? That
you
should be
can
0.
constrain it more.
Yeah. Point of honor.
Yeah.
Okay,
If we marginalize over the C3 terms.
I see. And so that's what this gives, but the CMP doesn't give us a stronger.
So we get this, and CMP gives.
Okay, that's what you said before. Yes.
So CMP gives a factor of
Okay, good.
5 better. Okay, this
So
was
the point is that in the next few years you could be able to go. More questions? Are there?
Right. I mean, with Giovanni, we're always around, and we'll be happy to take more questions.
Okay, well, thank you again. Thank you.